We will have our work cut out in this, the third lecture of the Relativity with a Flashlight series. At the end of the last lecture, we had met length contraction, a very important relativistic phenomenon. We will begin by describing that contraction, the same phenomenon, using an entirely different approach. Then, we are going to go ahead and state a new paradox, resolve it, and follow it up by resolving the paradox that we had talked about in the last lecture. We are then going to go on to show how Doppler factors for different observers combine, and this will give us a very quick way of deriving the relative velocity formula and the velocity addition formula. So there is a lot in store for us in this lecture, and let us just jump into it. As I have said before, in all subjects, especially in something as counterintuitive as special relativity, it always helps to have multiple ways of looking at the same thing. So let me now present one more way by going back to our old friend, the so-called Photon Clock. Remember, it was Alice who carries the clock here, and this clock has two mirrors spaced by L0, and Alice counts as a single tick on her clock the time it takes for a light pulse to travel from the bottom mirror all the way to the top mirror and back. Now, of course, according to Alice, this should take a time given by twice L0 by C, where L0 is the spacing between the two mirrors. Now, we are going to use the same photon clock which we had earlier used to understand time dilation, but this time we are going to use it to understand length contraction. For this, the setup is as follows. Alice is running towards the right with respect to Bob, who is observing the whole thing. But this time around, unlike the previous case when we were talking about time dilation, Alice has turned the clock on its side. So now instead of a bottom mirror and a top mirror, Alice actually has a left mirror and a right mirror. But of course, as far as she is concerned, the light pulse still travels a distance L0 to one mirror and back. So this is exactly the same as far as she is concerned. The time taken is again going to be twice L0 by C. Now let us try to figure out what the time taken will be according to Bob. But now let us not assume beforehand that the spacing between the two mirrors will be L0 when Bob looks at it. So just to be on the safe side, let's assume that Bob sees the spacing between the two mirrors to be L. Could be the same as L0, maybe it's different. In fact, we already know from the last lecture it will be different, it will be shorter. But we are not going to assume that at this stage. We are going to try to see whether our knowledge of relativity tells us that L0 and L are going to be different. In order to do that, let us take a look at this sequence of events. Light traveling out from the left mirror, which Alice is holding, going out all the way to the right mirror, bouncing back from there and coming back to her left mirror. Let us try to look at these events from the point of view of Bob. So this is what Bob is going to see. Bob, of course, is going to see both mirrors travel to the right, and light is traveling and catching up with the left mirror. By the way, everything is happening at a uniform speed. The only reason why you see the light pulse slow down or speed up is because I am controlling the frame rate in a non-uniform manner. And now, let's try to figure out how long will Bob say this thing takes. Well, according to Bob, the two mirrors were separated by a gap of L at the beginning. Now, the right mirror has travelled an extra distance given by Vt1, where T1 is the time interval which Bob sees, the time of travel for this pulse. And of course, in this time, the pulse has travelled a distance Ct1. So it's obvious from geometry that L is given by the difference between Ct1 and Vt1, and so T1 is simply going to be L by C minus V. At this point, it is quite natural that one might think that this argument is making a mountain out of a molehill, because all we are using here is a simple relative velocity formula that we had learned about in class 11. Alice is moving away from Bob with a speed v. Light is travelling away with a speed c. So the relative speed of light with respect to Alice is c minus v according to our class 11 formula. And you divide the gap L between the two mirrors by c minus v, and then you're done. That's your time taken. While this argument does give you the right answer, T1 is L by c minus v. After all, that's simple geometry. You cannot really escape that. The argument that this actually says that the relative velocity of light with respect to Alice is c minus v is quite wrong. It has to be wrong after all. If you believe in Einstein's second postulate, which says that the speed of light relative to every observer is c, then the question of it being c minus v relative to Alice simply does not arise. We will come back to this question of relative velocity later, but let me point out that the reason why this might mislead you into thinking that c minus v is actually the relative velocity is simply this. We are using a space measurement made by Bob between the two mirrors and assuming in our head that there is exactly the same gap which Alice will see between these two mirrors. Also, the time which Bob measures between the two events, light starting out from the left mirror, reaching the right mirror, we have assumed that Alice will see the same time gap. Now this assumption is something which is pre-Einsteinian. Before Einstein, we used to think that time intervals and spatial intervals are absolute quantities. All observers agree about how big they are. From our experience with relativity so far, we have learned that that is actually not true. So, if you were to try to conclude that c minus v is the relative speed here between the light pulse and Alice, where you would go wrong is that you are borrowing Bob's spatial measurement and Bob's temporal measurement as it is and using them as Alice's. This actually is exactly what gives us the v1 minus v2 relative velocity formula in classical physics. By classical I mean pre-Einsteinian physics. And this does not work in special relativity simply because the assumption that the space measurements and time measurements are the same for all observers fail and fail spectacularly. We will come back to this question of relative velocity later once again, but for the time being, let us continue with what's going to happen to this particular light pulse on its return journey. Of course, on the return journey, the light pulse is going to come and meet the mirror, the left mirror now. So T2, the time taken here, is again straightforward. When the second pulse started out, or when the pulse started out on its return journey, the gap was L. In the time T2 which the return journey has taken, according to Bob, Alice's left mirror has travelled a distance vt2, light has come back a distance ct2, and now from the geometry once again it's obvious that L must be equal to vt2 plus ct2, and hence T2 must be L by c plus v. So to summarize, for Bob, the outward journey of the light pulse took L by c minus v, and the inward journey took a time of L by c plus v. So total time taken, T1 plus T2, is twice L by c by 1 minus v square by c square. But we already know that the total time taken for this back and forth journey, according to Alice, is twice L0 by c. However, what we definitely should not do is equate these two times. Remember, we have already learned that observers who are moving with respect to each other disagree about the size of time intervals. Now let us quickly go back to our time dilation formula. Consider the events involved. Light is traveling out from the left mirror, going all the way to the right mirror. Now, as far as this pair of events is concerned, neither Alice nor Bob are present at both events. So, neither of them can actually use the time dilation formula for the first half of the journey. However, if you consider both halves together, then light has come back to the same position as far as Alice is concerned, back to her left mirror. Of course, light has not come back to the same position according to Bob, because Alice's left mirror, of course, has moved quite a lot in between. However, because Alice is present at both events, Alice's time measurement twice L0 by C is actually the proper time measurement. Bob's is not. So the two has to be related by the time dilation formula, and so you end up with the result that twice L by C by 1 minus V square by C square, which was Bob's time measurement between these two events, must equal Alice's time measurement twice L0 by C divided by the time dilation factor, square root of 1 minus V square by C square. And now, by simply cancelling out some of the factors, it's easy to see that L, the length which Bob sees between the two mirrors, is simply L0 times square root of 1 minus V square by C square, or our old friend, the formula L0 by gamma. So we have got the link contraction formula once again, but we have got it this time by using this simple clock, a photon clock where light just goes back and forth. I'm pretty sure most of you have actually caught on to this, but let me just stress once again, I deliberately looked at the entire back and forth journey of the light pulse, not just any one half of the journey, simply because then and only then can I use the time dilation formula, because if you consider the entire back and forth journey, the two events at the beginning and end of that are occurring at the same place with respect to Alice. This is something I could not have used for either half of the light pulse's journey. They were occurring at different places for both Alice and Bob. Now that we have derived the link contraction formula using two entirely different approaches, the K calculus on the one hand and this photon clock on the other, it is high time that I introduce you to one of the most famous paradoxes in relativity theory. We had already met a paradox in the last class and we have not resolved that yet. Remember the problem where Alice was seeing Bob's clock run slow, which is fine, but apparently Bob was seeing Alice's clock run fast. We will resolve that later on, but for the time being, let me introduce you to this particular paradox. This goes under various different names. It's called the barn and the ladder paradox and so on, depending on which book you're reading. For me, drawing a ladder is more difficult than recycling the drawing of the car that I had used earlier in a lecture. So I'm going to call this a car and garage paradox. So the setup of this paradox is something like this. Somehow I have had a huge windfall, maybe I've just won a lottery, and I bought a 5-meter long car. But the garage that I have is the same as when I was not so rich, let's say. It's only 3 meters long. So the question is, how can my 5-meter long car fit into my 3-meter long garage? That's impossible, you would say. But because we have learned a bit of relativity, we would know that this is not really impossible. All I have to do is drive my car fast enough so that from the point of view of somebody standing on the ground, my car would shrink. In fact, if I drove the car at 0.8 c, 0.8 times the speed of light, the link contraction factor would be 0.6, and that's exactly what will make my 5-meter long car fit into a 3-meter long garage. So, if I drive at 0.8 c, my car actually shrinks with respect to somebody who is standing on the ground, and so what that person should be able to see is that the front end of my car touches the back end of the garage at the same instant as the back end of my car touches the front end of the garage, and so it fits nicely in it. Of course, what happens after I hit the front end, what kind of disaster happens after that, let's not worry too much about this. Now, in case you're objecting that I couldn't possibly drive a car at 0.8 c, is simply too fast, let me just submit to you that the chance of my owning a 5 meter long car is almost the same as being able to find a car which can travel at 0.8 c. Anyway, this is a thought experiment, and as long as I'm not violating the laws of physics, there's nothing wrong with this. So my 5 meter long car fits into the 3 meter long garage. So, is that a paradox? The answer is no. There is no paradox here. It's something which is very counterintuitive, does not conform with what we think about as possible in our daily life worlds. And that's also quite natural. After all, speeds of 0.8 c are things which you do not see in your daily life world at all. But the paradox comes from the other point of view. All this was from the point of view of somebody who was standing on the ground next to my garage, and this person would say my car's front end hit the black wall of the garage at the same instant when my car's back end was in line with the front end. So my car fit into the garage, at least for that instant. But let's think of what will happen from my point of view. I'm sitting on the car, driving it towards the garage. But of course the car is not moving with respect to me. So my 5 meter long car is actually still 5 meter long. It's actually the garage which is traveling towards me which has become smaller. In fact, it has contracted by the same factor. It used to be 3 meters long when it was at rest with respect to me. But now that it is approaching me at a speed of 0.8 c, it contracts to a length of only 1.8 meters. So, from my point of view, the car fitting into the garage is simply impossible, because now is the garage which is actually shorter, and so even after my car's front end hits the back wall, my car's back end would stick out quite a long way. In fact, it would stick out exactly 3.2 meters. So this is where the paradox is. Not in the fact that a car becomes smaller when it moves, or the garage becomes smaller when it moves. The paradox is, one observer, the ground-based one, is saying that the car will fit into the garage, and another observer, namely me who is driving the car, is saying the car definitely cannot fit into the garage. Paradoxes are when you argue apparently equally correctly from two different points of view and end up with opposite results for the same situation. And this here is a paradox. The question is, which of our two views is correct? And the answer to that is a bit surprising. The answer is, both observers are correct here. Now you might find this unbelievable. How can the two statements that the car fits into the garage made by the ground-based observer be equally correct as my statement that the car definitely does not fit into the garage? To understand this, what we have to recall is another feature of space-time that we had derived in the last lecture. In fact, we had derived it sort of as a side effect of our calculation using k-calculus for length contraction. We had shown that two events which are simultaneous with respect to one observer are not necessarily simultaneous with respect to another observer who is moving with respect to the first one. We will explain exactly what this relativity of simultaneity has to do with this paradox soon. But before we do that, let me give you a different way of deriving this particular result. The relativity of simultaneity between two observers. Let us indulge in another thought experiment. Here we have our two favorite players, Alice and Bob, back again. And once again our protagonists have sort of switched places. Alice is the one who is doing the observing now, and Bob is running with respect to her towards the right. Now in this case, Bob also has an additional prop. He is carrying a pole whose length is L0, at least according to him, with flashlights attached at both ends. Just when he crosses Alice, Alice observes that the two flashes occur together. Now, you have to be a bit careful here. Alice does not see the two flashes together. Remember, Bob is just crossing Alice. So, one end of the pole is right next to her. The light of that flash will reach Alice immediately. The other end of the pole is at a distance L0 away. According to Bob, light will take some time to travel all the way from that flash to Alice. In fact, it will not take L0 by C, because remember, Alice does not see Bob's rod as having length L0. Bob's rod is moving with respect to Alice, so it's going to contract with respect to her. But be that as it may, Alice infers from the time at which she does observe the pulse that the two flashes had occurred simultaneously at a gap L from each other. What will happen, of course, is that before the right hand pulse gets to Alice, is going to meet Bob on the way. Let us try to understand what is happening from the point of view of both the observers. First, Alice's point of view. Note that as Bob is running, the instant Bob catches up with Alice, the two light flashes occur. Green one at the left end, which reaches Alice immediately. In fact, it also reaches Bob immediately. At T1 equal to 0 according to Alice, and in fact T1 prime equal to 0 according to Bob. What about the other pulse? The other pulse will take quite some time to reach Bob. The light pulse is travelling towards the left. Bob is travelling towards the right with a speed v. And the time which Alice will infer, at which the light pulse from the right meets Bob, has to be L by C plus V. Once again, this is not a relative velocity calculation, this is simply geometry. T2 is the time between the pulse setting off and reaching Bob, according to Alice of course. So CT2 is the distance which light has moved in that time. VT2 is the distance which Bob has moved towards the light source in this time. And the sum of these two must be equal to the gap L, remember, not L0, which Alice sees between her position and the point from which the light pulse started. Now, how does Bob view the same pair of events? As I said already, the light from the left flash reaches Bob immediately. After all, it's occurring at the left end of the rod which Bob is holding in his hands. So, to Bob, the left flash occurs at time t1 prime equals 0. What about the right flash? Now notice, Alice has already said that the interval between the left flash reaching Bob and the right flash reaching Bob is L by C plus V. The first event occurred exactly at 0 according to her. The second event occurred at L by C plus V. Now this is the time interval between these two events as measured by Alice. But these two events have occurred at two different places as far as Alice is concerned. But as far as Bob is concerned, both these two events have occurred at exactly the same place, namely where Bob is. So, Bob actually measures the proper time between these two events. So, since Alice has said that the time interval is T2, L by C plus V, Bob must say that the time interval is actually smaller. Moving clocks run slow, remember? And so Bob must say the time T2 prime at which the right hand flash reaches him is given by L by C plus V, that's of course T2, times square root of 1 minus V square by C square. Remember once again, it's Bob who is measuring the proper time, so the formula should be T2 prime by square root of 1 minus V square by C square equals T2, which we have just used in reverse here. So the right hand pulse reaches Bob at time given by T2 prime. The question is, how long did the right hand pulse travel before reaching him? As far as Bob is concerned, the answer is very simple. The right hand pulse started out from the right edge of the rod, and the rod has a length of L0. The time the light flash traveled, according to Bob, is simply L0 divided by the speed of light, that is c. Now, since we are writing everything in terms of Alice's measurements, let's rewrite L0 in terms of L. And that, of course, is given by the fact that L, the length of the moving rod, according to Alice, is L0 square root of 1 minus v square by c square. So L0 is L by square root of 1 minus v square by c square. And this is what the travel time for the second flash is according to Bob. So the second flash reaches Bob at time t2 prime. It must have travelled for a time given by L by c square root of 1 minus v square by c square according to him. So when did the second pulse start out? Remember, according to Alice, it started out exactly at time 0 when Bob was right next to her. But according to Bob, the second pulse started out a time given by t2 prime minus tau. t2 prime is the time at which it has reached Bob. Tau is the time for which it has travelled. So you have to take away tau from t2 prime to get the time at which the pulse started out. And it's a simple calculation which leads to the final answer, minus LV by c square square root of 1 minus v square by c square. Or, written in terms of the factor gamma, it's minus gamma LV by c square. So the conclusion is two events which Alice sees occur simultaneously, the two light flashes at two ends of Bob's rod, at a distance of L from each other, remember that's Alice's distance, is seen by Bob, somebody who is moving with respect to her, to occur at a time difference. The left flash occurs at t1 prime equals 0. The right hand flash occurs, the second flash, must have occurred at time minus gamma LV by c square. So two events which are simultaneous with respect to Alice are not simultaneous with respect to Bob. And we have recovered the formula that we had already discovered earlier using the K-calculus method, that the time gap between the two events as measured by Bob is minus gamma LV by c square. The event which is towards the direction in which it is travelling will be earlier according to Bob. So to summarize, the two flashes are two events which occur simultaneously according to Alice but at a distance L apart. According to Bob, the two events actually occur at a time interval of minus gamma LV by c square. The minus sign here simply shows that the event which occurs more towards the direction in which Bob is travelling, here to the right, actually occurs earlier as far as Bob is concerned. So this is something which, as we have said earlier, is at the very heart of relativity theory, is one of the most unusual results from relativity, that things which we had always taken for granted, the fact that simultaneity is absolute, two events which occur at the same time for one observer must occur at the same time for another observer, actually fails in relativity. And we have just found confirmation of that using a different approach. Let us now go back to what prompted us to look at relativity of simultaneity here. That is the question of the car and the garage. The question of whether it fits or does not fit. But let me just point out once again, what is important is what is simultaneous to Alice is not simultaneous to Bob. And simultaneity is relative. That is the take-home lesson from here. So, the resolution of the car and garage paradox. Well, as always, it makes things clearer if we think in terms of events. The two events that are involved in this particular issue about the car and the garage are as follows. The event A is the front end of the car touching the rear end of the garage. And event B is the rear end of the car touching front end of the garage. To an observer on the ground, these two events are simultaneous. The front end of the car touches the rear end of the garage at exactly the same time when rear end of the car touches the front end of the garage. So these two events are simultaneous with respect to the fellow on the ground. But they are not occurring at the same place, of course. Otherwise they would have been the same event. They occur 3 meters apart. 3 meters being the length of my garage according to somebody who is at rest with the garage. Now, from the car's point of view, these two events do not occur simultaneously. That's the point that we have been trying to make all along. What is the time gap between the two events? The time gap is given by L gamma V by C square. So L here is 3 meters, gamma is 5/3, V is 0.8 C. So if you use all of that and cancel out factors, you ultimately end up with a result that from the point of view of the car, the event A occurs earlier by a time given by 4 meters divided by the speed of light. 4 light meters, if you really want to use that unit. Now the important point here is this. The fellow on the ground says that the car fits into the garage because A and B are simultaneous. I, from the car's point of view, would say that event A has occurred 4 meters by C earlier, and remember the garage is travelling at 0.8 C with respect to me. So by the time the garage's front end goes and reaches the back end of the car, once again let me stress, is the garage which is moving with respect to me, not the car. That extra time of 4 meters by C is exactly what the garage needs to travel the extra 3.2 meters distance. 4 meter by C times 0.8 C is exactly 3.2 meters, and that is the length which I say is sticking out of the garage at the instant when my front end goes and touches the garage. So the question is now, does the car fit inside the garage or not? The answer is, it fits inside the garage from the point of view of somebody on the ground. It does not fit inside the garage from the point of view of somebody on the car. And there is no contradiction between these two statements, because the fact that fitting inside the garage is an absolute statement presupposes the notion that simultaneity is absolute, and we have just learned that in relativity simultaneity is not absolute. While we are at it, let me now describe the resolution to another paradox. This is the paradox that we discussed but did not resolve in the last video. Remember, this was a paradox where we were talking of Alice, where two clocks 6 light seconds apart, they were synchronized together, that they were set to 0 together, and Bob, who ran from one of the clocks, the one next to Alice, to the other one at a rate of 0.6 times the speed of light. So, the paradox essentially was this, that given Bob's speed, it's easy to see that Alice will say 10 seconds will elapse in Bob running from one location to the other, which means when Bob is right next to Alice's second clock, Alice's second clock will show 10 seconds, but using the time dilation formula, we can figure out that Bob, who is present at both the initial event, at which Alice's left-hand clock was showing 0, and the final one, is going to measure the proper time interval between the two events, and that is going to work out to be only 8 seconds. Now, there is no paradox in that. All that said was Bob's clock is running slow. However, Bob can also turn around and say, okay, my clock is showing 8 seconds, whereas Alice's clock is showing 10 seconds. That is, Alice's clock is running fast. Now, how is that possible? Because as we know, relativity does not distinguish between one inertial observer and another, and all moving clocks should run slow. So the question is, how is it possible that Alice's clock apparently is running fast? This, of course, was the paradox, and let me just discuss how to resolve this. As always, when you are dealing with some tricky situation in relativity, it is a very good idea to identify what events are we talking about. So, the first event here is rather easy to identify. It's that event where Alice's left-hand clock is set to 0. We are going to call this event A. In fact, Bob's reaching Alice happens at exactly the same point in space as well as time, so that does not count as a separate event. That's also part of our event A. The second event is the one where the whole thing ends, that is, when Bob has reached Alice's other clock. So this is our event B. Now, according to Alice, the time interval between these two events, TB minus TA, is 10 seconds, whereas according to Bob, the time interval between these two events, which we are writing with a prime, is 8 seconds. And this is exactly what our time dilation formula has told us. There is actually a third event here which needs to be identified very clearly, which is the event where Alice's right-hand clock has been set to 0. Now this event happens at exactly the same time as event A as far as Alice is concerned. After all, Alice is going to measure time intervals by comparing readings of these two clocks. So she has to make sure that the clocks read the same value at the same time. So TC, the time at which the third event has occurred, is actually 0, because that's exactly what Alice has also assigned to the first event. These two events are simultaneous according to Alice. Now the whole paradoxical situation arises because 10 seconds has elapsed on Alice's second clock. And it looks like 10 seconds has elapsed on Alice's clock, whereas only 8 seconds have elapsed according to Bob's. But that is not really quite correct. Because remember, when you say 10 seconds has elapsed in Alice's clock, what you're really referring to is Alice's second clock. The time interval that you're looking at is the time interval between events B and event C. So TB minus TC is 10 seconds. Now that's sort of consistent with what we have already said. After all, TB minus TA was 10 seconds, which is why Alice had concluded that Bob's run actually took 10 seconds. And since TC is the same as TA, TB minus TC has to be 10 seconds. But note that the time at which this third event has occurred is the same as the time at which the first event has occurred. TC is equal to TA, but that is true only for Alice. C and A are different events because although they happen at the same time, at least for Alice, they occur at different places, exactly 6 light seconds apart. Indeed, as we had learned just a few minutes ago, the two events A and C, which are simultaneous with respect to Alice, will not be simultaneous with respect to Bob. In fact, the time difference can be easily calculated by the formula that we had derived. The time difference as measured by Bob between these two events A and C is given by minus L gamma V by C square. So by putting in the values, what we get is L is 6 light seconds, that's 6C times 1 second. Gamma is 1.25 for this particular speed. V is 6C, 0.6C, and then you divide this by C square. So cancelling out the factors of C, what you end up with is minus 4.5 seconds. So what does this really tell you? It tells you that the event C, the event at which the right-hand clock of Alice has been set to 0, actually has been set to 0 according to Bob at a time given by minus 4.5 seconds. So the time interval between event C and event B, according to Bob, is actually not 8 seconds, not Bob's final reading, but 8 seconds minus 4.5 seconds. According to Bob, Alice's second clock had been set to 0 before he had reached Alice's first clock, 4.5 seconds before, and as a result, by the time he came abreast with the second clock, this one has already been running for a total of 12.5 seconds. And now Bob actually can say that Alice's second clock is running slow because whereas 12.5 seconds has actually elapsed, this clock is only registering 10 seconds as a time. This, of course, is completely justified by the time dilation result. Alice's second clock is registering the proper time, which is 12.5 seconds divided by gamma, and so it's registering 10 seconds. Everything works out fine. Both clocks are running slow according to the other person's reckoning. The whole crux of the paradox was that the two clocks which Alice used were synchronized with respect to Alice, but the synchronization is in doubt the moment some other observer comes in. In fact, this is why I personally prefer the K-calculus approach towards explaining relativity over Einstein's attempt to explain relativistic phenomena by putting clocks at every point in space and time. This is something we described in the last lecture. The point is, every observer has to have his or her own bunch of clocks at every point of interest, and each of these clocks have to be synchronized. And since synchronization involves the notion of simultaneity, two different observers will always disagree about whether the other person's bunch of clocks are synchronized or not. The K-calculus approach uses only a single clock per observer and infers times for events which occur elsewhere by using light signals which bounce back from that event. Since we are using only one clock per observer here, the situation is, at least to my mind, a lot easier to understand. However, situations like these where multiple clocks are used will arise several times in relativity, and as illustrated here, the best way to approach these things would be to clearly identify which distinct events are taking place and try to assign a timestamp to each one of them according to each observer. Now that we have taken a look at several of relativistic phenomena from different viewpoints, by using the K-calculus method or by using some other more physical, so to speak, approach, let us take a look at the phenomenon which started it all. As we have already seen, the Doppler effect is central to the basic idea that we have used in the K-calculus approach. We have already worked out a formula for the Doppler factor K in terms of the speed of the observer. We found out that K is square root of 1 plus beta by 1 minus beta. But let us just see how that will follow from basic time and distance considerations. Once again, consider our two friends, Alice and Bob, Alice in red and Bob in black running past her towards the right. And Alice is going to send out two signals to Bob, one after the other. The first one she will send out at time 0, but at that time Bob has already crossed her and is at a distance d from her. The second one she will send out at a time capital T later. Remember, these are times as measured by Alice. So, Bob is crossing Alice right now at this instant, which is t equal to 0 according to Alice. Alice has let go of a light flash, and that light flash travels towards Bob and catches up with him. So when does Bob receive the light pulse? According to Alice. According to Alice, Bob was at a distance of capital D when the light pulse was released. Light has travelled for a time t1, and this time t1 is found out this way. You just multiply t1 by c to get the distance which light has travelled, that's ct1, and Bob has travelled an extra distance of vt1 in addition to the original distance d which he was at. So it follows that d plus vt1 equals ct1, and hence t1 is d by c minus v. This should not surprise you. We have already seen this argument being used for our Photon Clock explanation for the length contraction. So this is when the first pulse reaches Bob. What about the second pulse? Now the second pulse actually starts out at a later time. Okay, so it has started out at a time capital T later than the first one, again according to Alice. So, as far as the second pulse is concerned, when it started out, Bob was at a distance of d plus v times capital T away from Alice. So, if the time taken for the second pulse to catch up after it is released is t2, then t2 can be easily found out by a similar calculation to be d plus v capital T divided by c minus v. So the question now is, what is the time gap between these two pulses as observed by Bob? But let us first figure out what the time gap is as observed by Alice. Alice sees the first pulse reach Bob at the time t1. The second pulse actually reaches Bob at a time capital T plus small t2. Small t2 is the time which light is traveling here. Of course, since light had already started out at time capital T later, the time at which the second pulse reaches Bob is capital T plus small t2. So time gap between these two events as seen by Alice is simply the difference between capital T plus small t2 and small t1. And it's a matter of very simple algebra to work this out, and this is going to turn out to be capital T by 1 minus V by C. Now this is a time interval between two events. Alice's first pulse reaching Bob and Alice's second pulse reaching Bob. Does Alice measure the proper time between these two events? Of course not. Alice is not present at both events. But we do know of an observer who is. That's Bob. Bob is present at both events. So Bob actually sees a time gap which is the proper time interval. And because there's a proper time interval, Bob's time interval is smaller by a factor of square root of 1 minus v square by c square. So time interval as seen by Bob is delta t Alice times square root of 1 minus v square by c square, and hence turns out to be, after a very simple calculation, t by square root of 1 plus v by c by 1 minus v by c. So as promised, what we have found out is this. When Alice releases light flashes at a time interval capital T, according to her clock, Bob receives them at a time interval according to his clock of capital T into square root of 1 plus v by c by 1 minus v by c. So, and this is exactly what the Doppler effect says. Time intervals increase by this factor which we have been calling the k factor so far. So k factor is given by square root of 1 plus v by c by 1 minus v by c. This is the factor by which time intervals increase. Frequencies, of course, decrease by the reciprocal of the factor, which is why when an observer is moving away, for the k factor is bigger than 1, but the frequency gets diminished. So an observer sees the light pulses at bigger time intervals, hence at a lower rate. Now that we have established, yet again, the relationship between the Doppler factor, the factor by which time intervals increase, and the speed that the observer has, let us put this to use to figure out a very important result. We have been talking about that off and on, the velocity addition formula according to relativity, and we do expect it to differ from the standard result that we studied in class 11 of u plus v being the result for a relative velocity. Okay, let me just be a bit more clear about this. The problem that we are addressing here is as follows. Here we are talking about three observers, Alice, Bob, and Charlie has joined the gang here. Bob is moving at a speed v with respect to Alice. Charlie is moving at a speed u with respect to Bob. The question that we are addressing here is this. What is the speed of Charlie with respect to Alice? This speed, w, is what we are trying to find out. Classical, that is pre-Einstein physics, would have told us that w is u plus v, but we already know that at least in one case where Charlie, instead of being an observer, is a flash of light, so that u is c, the result u plus v simply cannot be correct because the flash of light will not only move at a speed of c with respect to Bob, it will also move at a speed c with respect to Alice, not c plus v. So what we are going to do now is try to figure out exactly what the correct relativistic formula is. And for that, all you really need to worry about is this. Instead of saying that Bob has a speed with respect to Alice, we could equally well say Bob has a Doppler factor, let's say k1 with respect to Alice. And Charlie has a Doppler factor with respect to Bob. What that means essentially is this. If a sequence of light pulses traveling towards the right crosses Alice at time intervals of capital T, then those pulses will reach Bob at a time interval of k1 times t. Now you can say Alice sends out these two signals at time t apart, or you could just imagine two signals crossing Alice, coming from the left and crossing her and going to the right. But when they cross Alice, the time interval between them is capital T. Bob gets them a time k1t apart, as we have said, where k1 of course is square root of 1 plus v by c by 1 minus v by c. But as far as Bob is concerned, you could just as well say that Bob has sent out these two light signals at a time interval of k1t, according to Bob's watch. So when will Charlie receive them? Charlie will receive them at a time interval of k2 times whatever interval Bob sends them at. That's what Charlie's Doppler factor with respect to Bob means. So Charlie gets the light pulses at an interval of k2 times k1 into t. So Charlie's Doppler factor with respect to Alice is simply given by k1 times k2. So Doppler factor of Charlie with respect to Alice is nothing but Doppler factor of Charlie with respect to Bob times the Doppler factor of Bob with respect to Alice. This follows immediately from the definition of the Doppler factor. Now, from what we have seen so far, it should not be an exaggeration to say that Doppler factors are in fact a lot simpler and superior way of expressing the rate at which one observer moves away from another compared to our more familiar quantity, the speed. Measuring Doppler factor is actually quite easy. All you have to do is send a couple of light pulses which crosses both the observers and ask them to report the time according to their own wristwatches between the two pulses crossing them, and the ratio of these two time intervals is simply the Doppler factor. What is also quite useful is the fact that the way in which Doppler factors compose when you have multiple observers involved, like here, is that they simply multiply. So Doppler factor composition is simple, it's just a multiplication. By the way, there is another quantity which is often used in relativity to quantify the rate at which one observer is moving with respect to another, and that's called the rapidity. Rapidity happens to be nothing but the log of the Doppler factor, and that is obviously a convenient thing because Doppler factors multiply means rapidities, their logarithms, add up. What does not add up are velocities. So our velocity addition rule really is not addition, so to speak. But now that we have this result that Doppler factors multiply, we can use that to figure out exactly what the combination rule is for velocities. To see that, all you have to do is replace K3, Doppler factor of Charlie with respect to Alice, by square root of 1 plus W by C by 1 minus W by C. Remember, Charlie is moving at a speed W with respect to Alice, which is what we want to figure out here. Similarly, K1, which is Bob's Doppler factor with respect to Alice, is simply square root of 1 plus V by C by 1 minus V by C. And K2, Charlie's Doppler factor with respect to Bob, is square root of 1 plus U by C by 1 minus U by C. So what we end up with is this formula. So K3 equals K1, K2 translates to this relationship between velocities, and now you square the result and then use our very old friend componendo dividendo, and that immediately gives you the result that W works out to be U plus V by 1 plus UV by C square. the standard velocity addition rule that we had learned in class 11 would have told you that W is U plus V. Notice that for Dirichlet velocities where U and V are very much smaller compared to C, the denominator is very nearly 1. The difference from 1 is negligibly small, and in such cases W really works out to be U plus V, which is what explains why we have not been able to see the difference in our daily life world. But just as a check, if Charlie happened to be replaced by a flash of light, that is U had been C. This gives us for W the result C plus V by 1 plus CV by C square, and simply cancelling out factors will tell you that W works out to be exactly the same as C. So, the speed of light is the same for Bob as it is for Alice, which is what, of course, our basic postulate of relativity had told us. Once we have derived the velocity addition formula, its counterpart, the relative velocity formula, comes in almost for free. Just to see how the things are connected, let me rewrite the derivation of the velocity addition formula, at least the salient parts, using a slightly different notation. I have written Kc by A to denote the Doppler factor of Charlie with respect to Alice. And what we had worked out right now shows that Doppler factor of Charlie with respect to Alice must be equal to the Doppler factor of Charlie with respect to Bob times the Doppler factor of Bob with respect to Alice. And this, when you translate to the corresponding velocities, the velocity of Charlie with respect to Alice being W, velocity of Charlie with respect to Bob being U, and velocity of Bob with respect to Alice being V, translates to W equal to U plus V by 1 plus UV by C square. In the case of the relative velocity formula, the setting is slightly different. Here you are supposed to know the velocity of Charlie and Bob both with respect to Alice, and from that you want to calculate the relative velocity of Charlie with respect to Bob. In the language of Doppler factors, this is equally simple. The formula that we had written down earlier can be immediately rewritten in the form Doppler factor of Charlie with respect to Bob equals that of Charlie with respect to Alice divided by the Doppler factor of Bob with respect to Alice. And if you just carry out the same kind of calculation using componendo and dividendo that we did a while ago, you will find that the velocity of Charlie with respect to Bob, the relative velocity, which I am calling U prime, is given by U minus V by 1 minus UV by C square. So the two formulas are very, very similar. Classically, what used to be U plus V, the velocity addition formula, has become U plus V by 1 plus UV by C square. And similarly, the relative velocity formula, which classically was U minus V, has become U minus V by 1 minus UV by C square. Let me end today's lecture with a challenge. The challenge is simply to explain the relative velocity formula using the basic phenomena of relativity that we have already learned about. That is, using time dilation, length contraction, and the relativity of simultaneity. I am not going to show you how that is done, because that, of course, is a challenge for you to think about, at least until the next lecture. But just to sort of give you a feel of it, let me explain how this thing works in the familiar classical case. Here we have Alice, Bob and Charlie. And Bob and Charlie were both at the same location as Alice, but they are running at speeds of V and U with respect to Alice, both to the right. So at a time t, as registered by Alice's clock, or rather clocks, which she has placed at various different locations, Bob is at a distance Vt from Alice, Charlie is at a distance Ut from Alice. The question is, how far away is Charlie from Bob? And from that we should be able to figure out what the velocity of Charlie is with respect to Bob. Now, in order to answer the question how far away Charlie is from Bob, all you need to imagine is Bob is holding up a ruler, the red rectangle in your picture, and that stretches all the way from his position to Charlie's current position. So, the length of that ruler, according to Alice, is simple. Alice knows that the right end of the ruler is where Charlie is, and that is at UT. She also knows that the left end of the ruler is where Bob is, and that is at VT. So length of the ruler, according to Alice, must be U minus V into T. But how long is the length according to Bob? Now in pre-Einsteinian physics, length measurements were absolute. Whatever Alice measures must be the same as whatever Bob measures. So in pre-Einsteinian physics, the length of the ruler according to Bob must also be the same. So in pre-Einsteinian physics, Charlie would have been exactly U minus V into T distance away from Bob. And then the time taken for Charlie to get to this distance from Bob, remember they were all together at Alice's origin at t equal to 0, is a time t according to Alice again. So the time here, t, A is just t, that's what Alice has measured. This is the time interval between their all being together and their current locations right now. But again in classical, that is pre-Einsteinian physics, time measurements are absolute, so whatever measurement Alice makes must be the measurement that Bob makes. So Bob would also say that this distance of U minus V into T has been achieved by Charlie in a time given by T. So the velocity or relative velocity of Charlie with respect to Bob in classical theory would simply be the ratio of these two quantities, U minus V into T by T, and this would immediately give us U minus V. So this of course is the pre-Einsteinian version of the formula, which is a very good approximation to the actual formula U minus V by 1 minus UV by C square for velocities which are small compared to the speed of light, but still is not the exact relativistic formula. Now the challenge that I have for you is this. Use arguments exactly like the one I have given you right now. Use the fact that moving lengths contract, moving clocks run slow, and even clock synchronization would have a problem because of relativity of simultaneity. And using all these, try to understand for yourselves why U prime is actually U minus V divided by 1 minus UV by C square. It's a rather interesting thing to work out on your own, and if you manage to do that, it's going to give you a much better understanding of all these relativistic phenomena that I'm talking about than seeing the derivation worked out by doing some algebra on a piece of paper. In the next lecture, we are going to talk about other fascinating aspects of relativity. We are going to talk about the Lorenz Transformation, which people usually start discussions of relativity with. And then we are going to go on to use the Lorenz transformations to show how all the phenomena that we have learned about so far work out. That would be more like a traditional relativity course workflow. We would also try, if time permits, to answer this very pertinent question: can things move faster than the speed of light? If no, why not? But all that is for the next lecture. Bye till then.